And welcome. First off, note this meeting is being recorded, and we hope to be able to make these recordings available sometime in the next week or so after we have a chance to quickly review them and make sure that nothing that was NDA protected accidentally made its way into the conversation. We welcome you today on our panel on U.S. federal agencies, Exascale application and software needs. I'm Susie Titchener with Oak Ridge Lab, and with my colleague David Martin at Argonne, we co-manage the ECP Industry and Agency Council, which is an advisory council to the ECP leadership. And we've invited our agency members to talk to us today about their Exascale needs and requirements and what they see in the future for their agencies for Exascale applications and software. So we've got a really great session today with great folks, and we're just going to ask that all of you manually mute and unmute yourselves so that when we get to the questions, it's just a lot easier for folks to be able to jump in. We'll start off and have 3 presentations, and each speaker will leave a few minutes at the end for some quick questions. So that they don't get lost in the shuffle here. And then we'll take a pause and have some dialogue with Eric Drager and Mike Haru from ECP. And then we'll pick up with our other presentations and then finish out with a discussion with those folks and with all of the presenters together. And we'll also monitor the chat for any interesting questions that come up. So please feel free to use that. David?
Great. So the way that we're going to do this is to have some short talks by our 5 agency members or representatives of those members from the Industry and Agency Council. Everyone will have kind of 12 minutes to talk, and maybe a couple of minutes at the end of your talk to do some Q&A. And Susie and I will kind of keep time on you and say something when you're getting close to your time. We'll have a few of the talks and then we'll stop a little bit just to have some open discussion that Eric and Mike are going to lead. And then at the end, Eric Drager, who is our Deputy Director for Application Development, and Mike Haru, who's the Director for Software Technology, will lead us in kind of a discussion and then close us out in about 2 hours. The one thing to note is that we'll ask you not to interrupt during the talks, but there'll be time for questions and answers. But please post anything you'd like in the chat. And Susie and I will make sure to bring those up. If there is a question that is burning and you don't want to forget it, feel free to put it in there. Though we will allow you to unmute if you would like to ask the question, so you don't have to do everything through chat. The slides that I have are posted in the box folder that I just posted in the chat, and that should be available for people to see, and I will update those as I get slides from people. So I think that's about it. I think our first speaker is Fran Hill, and Fran, I believe I'm gonna run the slides for you. Fran is a co-chair of our Industry and Agency Council and from DoD, and I'll let you do a further introduction of yourself, Fran.
Thanks, David. I appreciate it. Well, good morning, everybody. As David said, I'm Fran Hill, and I am the Chief Scientist for the DoD High Performance Computing Modernization Program. It's my pleasure to be here to talk to you about what we're doing. And if we could go to the second slide, I guess. We don't really need to see the...
Let's see.
So I was going to start off by telling you a little bit about HPCMP. For those who are unfamiliar with us, we are the providers of computational resources, and I do mean high performance computational resources, to the Department of Defense. We provide resources to all 3 services in most of the agencies. We've been around now since about 1995, and interestingly, we still have a few people who were there in the very beginning, which I find kind of fascinating. So we've had a long history of delivering HPC to the Department of Defense. Physically, we have 5 data centers that are scattered around the U.S. One of the data centers is here in Vicksburg, Mississippi, which is where I sit. And it's also where the headquarters for HPCMP sits as well. So I'm not seeing a slide yet.
Yeah, sorry to interrupt. We can't see your slides.
Oh, you're actually not seeing them? Okay.
Yeah.
We are seeing, I think, the wrong window.
Oh, okay. All right, let's try this.
Much better.
Does that look better? Great.
So a few things to note about our organization, because we cut across a big chunk of Department of Defense, our software requirements are highly diverse. Fortran is still dominant, and I don't see that changing anytime soon, though, you know, truthfully, other languages are starting to creep in there, but Fortran still is the one that most people use. Our software investments over the last probably 5 years have been somewhat lacking, mostly due to budgetary issues coming through the Department of Defense. So I'll say a few more words about this, but our biggest investments tend to be in our Create suite of software, Create standing for Computational Research and Engineering Acquisition Tools and Environments. And boy, is that a mouthful to say. Much like, you know, we hear with ECP, we fully embrace the fact that the viable path to Exascale is going to require the use of accelerators. Our problem is that our user community has been very slow to adopt this technology. Next slide, please. Oops. So I had to put this up just because this is also our largest system that we have currently in our footprint is called Narwhal. And this is a Navy system, and it sits down on the Mississippi Gulf Coast. And so you can kind of see sea creature, Navy, that's the way they name them currently. So I had to brag about that. It's not large by ECP standards. It has about 290,000 compute cores. Next slide, please. So our software investments are in 4 different areas. I've already mentioned the Create suite, and Create is tools that are used by the acquisition engineering community to help design the next generation weapon systems. There's a component that looks at designing air vehicles, both rotorcraft and fixed wing, ships, RF antennas, and ground vehicles, and also one that's sort of a catch-all that looks at meshing. The second item that we invest in is in PET, which is our user productivity enhancement and training piece, and that's where our SMEs sit. And I'm going to say a little bit more about that on a future slide. We also have sort of an ad hoc capability, which we call institutes, which are focused cross-service investments that seek to fill in some of the gaps that we might encounter in important mission critical programs for the Department of Defense. And then our largest users of resources, and this of course is going to confuse people here because we call it Frontier, not to be confused with what that means for DOE, but our Frontier projects are the ones that are probably closest to being Exascale. They tend to use on the order of hundreds of millions of core hours per year, and they tend to be 3 to 4 years in length. Next slide, please. So I just wanted to give a little bit of a shout out again to Create. Create has been around since about 2008, and there've been a lot of adoption across both, not just government, but also industry. It's a very important tool, and according to this slide, this was as of August of last year, there were over 3,000 active licenses. Create is free, but it is ITAR restricted, and there is registration required and whatnot. So next slide, please. So I wanted to say a little bit more about PET, which is, as I said, our performance enhancement and training team. This is where our subject matter experts sit who have the ability to help our users implement things like accelerators as we go forward. It's a limited resource, so we manage it very carefully. And how we manage that is that user who wants help with their code, whether it's just to tune the performance or figure out a bug or whatever, or as we keep encouraging, to see about how to implement GPUs into their code. What happens is a user has to actually make a formal request, which is a small proposal called a mission project. These mission projects are reviewed by a technical board for computational merit and for DoD impact. So we wish we could accommodate every one of our users who has a request, but we have to be a little bit strategic as we go forward. Next slide, please. The institutes, as I said, are sort of an ad hoc ability that we have. We are finishing out the last of the 2 institutes that we've had going for the last couple of years. That last standing institute is a hypersonic vehicle simulation institute that's run out of the U.S. Air Force Academy. And it's looking at some sort of basic still work that's being done in the hypersonic arena. And the other institute, which I think finished at the end of the calendar year last year, is an Institute for Image and Sensor Exploitation that's run out of the Air Force Research Lab at Wright-Patt. This is probably the biggest success story that we have in implementing GPUs in our footprint. They've done an awesome job, and unfortunately what they do is classified, so I can't really say much more about it, but to say that there's certain parts of their program that I believe they are claiming something on the order of like more than 1,000 times speed up by implementing GPUs. So we're really excited for that project, and probably they'll be submitting a new institute soon. Next slide, please. Our frontier projects, these are always interesting. They tend to be a mixed bag. I did a quick search to see sort of, what we currently have. And in fact, we're in the season where we're looking to review the next suite of proposals. I think we have 11 proposals that came in, looking at what resources they will get for the next FY. As one can imagine, we have currently 16 active projects, 11 of which are in the area of computational fluid dynamics. And of those, I think 2 of the 11 actually are looking at GPUs. So that gives you a sense of how much we're not actually employing GPUs in the path forward. We have 2 projects that are in the area of climate, weather, ocean, 2 that are computational structural mechanics, and then 1 computational chemistry and materials. These 16 projects together account for about 1/4 of our allocated resources across HPC&P, which is just a tad under 2 billion core hours per year. Next slide, please. So one of the things that we've really been pushing, because it's really the only thing that we have a lot of wiggle room on, is strategically using our subject matter experts who provide help to our user community. They've been very much in trying to incentivize our user community. We actually give a little higher priority to a mission project if a user says they're interested in implementing GPUs. Also through PET, there are attempts to try to modernize, I guess is the best way to say it, our user community by offering training courses on things like Julia. And we've also started to partner with industry. For instance, NVIDIA has had a couple of hackathons with the Kestrel code that comes out of the Create suite of software. Next slide, please. And I think this next slide is my last slide. So where do we need to be going is the big question here. And the 2 things that I'm going to leave with you is that we need to talk about strategic leveraging, and we need to talk about partnering with other agencies. There are a lot of things out there that we're aware of in HPC&P, but we're not really vested in how we would implement that in our footprint. Things like the LLVM compiler project. Flying sounds like it could do a lot of good stuff for us, but I keep hearing sort of mixed reviews. Lessons learned from what Mike Carew and his team has done in E4S would be very helpful to us. looking at the Rose compiler framework, which is something that I don't know a whole lot about. So there's a lot of possibilities out there. So that I leave you that's the two things that I'm hoping that we'll have some forward momentum as we go forward. Thank you. I'm happy to take questions.
Thanks, Fran. That's perfect. So we have a couple of minutes for questions around Fran's presentation or feedback.
Kirk, I think you put one in the chat. You want to pipe up here?
Yeah, so we've had some conversations around leveraging Create and in particular the capstone geometry and meshing routines and such. But as you mentioned, there are ITAR and CUI kinds of restrictions that make it more complicated, particularly if it's not relating to a direct contract. And yet those seem to be potential opportunities to have the community benefit if it's not encapsulating some kind of sensitive information. I know there was a DoD.mil open source kind of environment at one time being discussed. Is there a path for some of these to be more widely used?
So the quick answer to that is that there is a not as protected, but it's probably the correct way to say it, version of the Create software that runs under the name of Genesis. And that's what's used in universities and other places where they're training the next generation of engineers and scientists to use this stuff. So if you're interested in understanding or getting connected with the Genesis folks, please send me an email. I'd be happy to make that connection.
I think you had a question also.
Sorry, was that for me?
Yeah, go ahead.
And then
Yeah,
you are great. And then Koti also had a question after you.
Oh, and then Doug can go first. Okay. Fran, I think you mentioned that was you were having 1 billion, or was it 2 billion core hours per year as a capability?
So the 2 billion core hours is about a quarter of our allocatable time, and that's what is dedicated to the frontier projects.
Okay, great. So you have about 8 billion overall.
Right, and we're about to move up to about 12 billion, I think, beginning in the fall.
Okay, great. Thank you. And yeah, similar to Rick, so I'm with Boeing. We certainly would also like to learn more about this Genesis project. I certainly see quite a bit of usage of Helios and Kestrel on our systems, but yeah, if we could expand the usage, that would be good.
Yeah, I'd be happy to make that connection.
Thank you.
Good.
Why don't we switch over to you?
Yeah.
It's okay. Susie, can you hear me, Fran?
Yeah.
Yep.
Hey, Fran, I'm going to cheat. I've got several small questions. Okay. What are the size of your Create teams? And just in general?
So I think across all the different areas that are part of Create, I think it runs about 200 people, something like that.
Okay, and that's the number of staff for several teams, right?
Yes.
Okay. Your institutes, can you give me a sense of the scope of the institutes? Because you said they were cross-cutting.
So when you say the scope, do you mean what the topic is, or
what sorts of things are they focused on? Correct.
So for instance, the hypersonic weapons development or vehicle simulation actually was a consortium using a bunch of folks from academia looking at some sort of basic, and I can't even think of what, I'm going to blow it if I say it wrong, but because it's academics, it's not classified in any way. So it's some basic CFD ideas moving towards hypersonics.
Okay. And then Fran, I'll tee this up maybe for Mike on LOVM. I think the area that we're really focused on is the front end for Fortran, to some extent the back end. But if you think about, all the vendors are either in the process or very likely to be in the process of plugging in a proprietary back end, then I think what we'd want to do with you is where possible, get a snippet of your Fortran code and see if our front end can process it well. I think some Fortran-based proxy apps might be a good place to start, but I'll defer to Mike.
And I think that's a great.
It would be nice to follow up on, engaging more of your code base in the, testing. There are a lot of Flang tests already, but I'm not sure that there's a lot that focus on the specific expressions your teams would use. And that stuff can be done today using for CPUs. The GPU version of Flang, which is the with OpenMP target offload, that's still in the works, and that's still some time away. But that, I think, is a really important development for the community as a whole, especially people that have a large Fortran code base. It's a viable path, for using accelerators.
I agree, and luckily we do have a fairly robust suite of what we call mini apps, which are kernels from these different things. So I think it would probably be a pretty easy slam dunk to try some of this. So it's definitely something I think we've talked about putting together a workshop at some point, and that might be a very useful thing to look at.
We should get those. Okay, thanks, Fran.
Thank you.
Okay, so we should probably stop here. So we will have lots of time at the end to discuss. Jeff, are you up on video and audio now?
Can you hear me now?
Yeah, you sound great.
Okay. Overcoming that technology obstacle. Good morning. I'm Jeff Durakta, and I'm lead for the Modeling Systems Division with NOAA's Geophysical Fluid Dynamics Lab in Princeton, New Jersey. While NOAA has an extremely diverse set of I need to get these up right. Let me share screen. Go. While NOAA has an extremely diverse set of missions, I'll touch on areas covering weather and climate research, as well as NOAA-gathered Earth system satellite data. First, I'll give a high-level statement of the problem, at least as the World Meteorological Organization perceives it. Next, I'll provide a quick sample of NOAA's current work to address the problem. Finally, I'll discuss what I perceive to be a problem largely unaddressed by current exascale activities. The problem, as summed up by the WMO, is really pretty simple. Urgent action is needed to overcome serious performance limitations that threaten the ability to run cloud-resolving global weather and climate predictions needed to serve society. So here are some of NOAA's current efforts to address the problem. This first slide summarizes a project to assess whether computational stencils used in many parts of Earth system modeling are even amenable to performant GPU programming. The GT4Pi domain-specific language under development by the Allen Institute for AI, they go by AI2, in collaboration with a number of organizations that include NOAA, provides a tool for such research. The DSL is expressed as Python. It supports retargetable backends, currently GPU and CPU, and year-over-year progress for GPU performance has been promising. We're now at 3.5 to 4x speed up on the GPU versus the original Fortran on some x86, which I don't know. We note, however, that the performance for the CPU target has received no attention yet and is lagging. Support for CPUs is a must, as code changes for the National Weather Service require an enormous amount of vetting, and the procurement cycles for NWS systems are quite long. The next set of slides cover possibilities for new and improved science. I'll be moving through them quickly. So the goal is of this section is to provide a flavor of what's going on, not the details. The Great Code is a flexible line-by-line radiative transfer code written to exploit the massive data parallelism provided by GPUs. It is written in C and CUDA-C and supports Fortran and Python bindings. It can target CPUs as well as GPUs. It can run in a standalone mode as well as callable by concurrent nested OpenMP within the GFDL modeling framework. The project depicted on this slide is machine learning at high model resolution to support subgrid corrections at much lower, less costly resolutions. This work is a collaboration between AI2 and my lab. Note that the FV3 GFS is the National Weather Service version of the GFDL FV3 Atmosphere Dynamical Core, and the SHIELD model referenced here is another version of the same FV3 DICORE. Not to be outdone, there are various efforts within our ocean modeling community to apply machine learning. This first slide depicts an effort to apply ML to the problem of vertical mixing profiles in the ocean surface boundary layer. This next slide, an even more ambitious project in my opinion, depicts the use of manifold learning techniques to infer ocean subsurface dynamics from surface data. Of course, land modeling is not to be left out, and so we have worked to apply machine learning to enhance mechanistic land parameterizations. And while not on this slide, there's also work to apply ML to the problem of land model spin-up. Finally, I would be remiss if I didn't mention work to apply ML and AI to the vast and ever-increasing volumes of data associated with NOAA's Satellite Data and Information Service. Additionally, there are efforts to make this data much more available through cloud services. And with this version of speed dating, I hope that this sprint gives a feel for what NOAA is doing, what is chasing in the exascale era. So in summary, progress for Earth system modeling applications harnessing exascale technology is accelerating. Sorry about that. So now my soapbox. Workflows in the exascale era, the problems left behind. Earth system modeling activities require substantial pre and post processing. While model output is not generally useful for Earth system prediction nor science insight. While the investment in exascale hardware and software has been large, the total cost to insight has yet to be addressed. And we'll use my Earth system workflow as a case study. On the left, this slide depicts the GFDL ESM workflow running on the 144,000 some odd core system Gaia, housed at Oak Ridge National Lab. At any time, the workload is comprised of 20 or more separate experiments running anywhere from 2,000 to 20,000 cores. The jobs are self-resubmitting and running all the time the system is available. Each experiment generates output measured in hundreds of gigabytes per model year with a throughput of 5 to 15 model years per day per experiment. As depicted on the right of the diagram, the output flows back to the GFDL for post-processing into the scientific products used for research. Model output is broken into separate file streams based on a notion of model component, such as atmosphere, land, ocean, etc. Each component represents an ongoing stream of post-processing and therefore an ongoing stream of jobs through the post-processing cluster. The coupled model intercomparison project version 6, which wrapped up now about a year or two ago, depending on how you measure things, provides a significant case study. During the years of model development, the runs described produced tens of post-processing jobs per model year and processed tens of variables per job. CMIP6 production, however, led to an order of magnitude increase both in the number of job starts per model year and the number of variables to be processed per job. From a scientist's perspective, they were just doing more of what they had been doing for the last 3 years or so. From an infrastructure perspective, however, The production runs stress the post-processing system in almost every dimension of hardware and software. The issues that crawl out of the woodwork with precipitous scaling always seem to catch users by surprise. Recently, we've introduced the vast solid-state cluster global file system. As moving data into the node local storage for further processing and then into archive for preservation comprised 40 to 60% of the post-processing wall clock, the cluster shared file system offers the potential to greatly reduce post-processing costs. On the other hand, the guaranteed not to exceed improvement is no more than a factor of 2. Paraphrasing a colleague at the National Weather Service, I reduced my model cost to 0 and still have 60% or more of the time to solution left. And so this is the issue. One of the hurdles that remains largely unaddressed at the launch of the Exascale era is the total cost to insight. So in summary, NOAA is making strides towards harnessing GPU-capable technologies for Earth system modeling. But producing data is not the problem and really hasn't been for a long time. Pre- and post-processing costs remain high and to date have not been addressed by exascale computational science research. In this exascale era, Earth system modeling, and I suspect other branches of research, need more attention to the total cost to insight. My thanks to those whose materials I've used to develop this presentation. And I'll take any questions now.
Thanks, Jeff. Excellent.
Okay, how do I get out of this? Stop. There we go.
Hey, Jeff, this is Doug. Can you hear me?
I can, Doug.
Yeah, so you make some good points. It's clear that ECP needs to expose more of what we're doing in this area. We have several projects looking at workflows. I'm not going to claim that they are subroutine answer for you, but I think we do need to talk to you face to face, understand what we have, if anything, that might be helpful, and get a better handle on your requirements. I will say that for system procurements, we need to look more closely at workflows, being the metric. So I certainly don't disagree. Thanks, Jeff.
Sure. My observation on that is, and I've had to think through this a little bit, is that a lot of what ECP has done for NOAA is a demonstration of capability, that it can be done. The risk in investing and having something not turn out is, well, you all have accepted that risk, and in some cases, it's not going to work out. NOAA is much more resource limited and therefore much more risk adverse. The fact that you all have demonstrated the application of GPUs lets NOAA know that, hey, it's possible we can do this. I would say the same is true of, not so much the workflow infrastructure software. That exists, and implementing a workflow is, how shall I say this? There are various engines. You still have to implement your workflow in them and make it robust. But it's the underlying technologies that will improve, reduce data motion, make the processing more at the point of production. All of these sorts of things are technologies I just can't get my hands on.
Okay, that helps, Jeff. Again, really good fodder for much deeper discussions. Thanks.
Other questions?
I'll just mention that this is an area of great interest to us, and it comes up increasingly, and we have spots of efforts going on at the various leadership facilities. But there's not we have this ExaWorks project, which is focused in as a holistic multi-institutional project, but I don't think it's addressing all of the scope that you expressed at this point, Jeff.
One of the challenges that I didn't mention is that, our archive is at, gosh, it must be heading towards 300 petabytes and growing at a frightening pace.
Good. Well, we'll have more time to discuss this at a little break-in
Thank
at the end. So stick with us. Piyush, are you ready?
Yeah, let me see if I can share my slides. Can you see my slides?
We do.
Yes.
Okay. Thank you for inviting me to this panel. My name is Piyush Mehrotra. I'm the chief of the NASA Advanced Supercomputing Division here at NASA Ames in the Bay Area, California Bay Area. So just to give you a little sense of where we are at, we've got multiple systems all in the sort of petaflops range. And just as a background, we are the premier supercomputer center for the whole of NASA. So the domain includes things like aeronautics, it includes earth science, helio, planetary, astrophysics, and also obviously space operations and design of vehicles for space operations. So a couple of years ago, we had a requirements workshop, and generally it's very difficult for folks to come up with their requirements, but at least for some of them, I was able to extract some of the requirements. And I don't want to go through each of these, but just to give you a sense of the different domains. And we're looking at least a few of the applications needing Exascale by the 2030s, including a couple global atmospheric and ocean modeling like Jeff was talking about for weather modeling. Retropropulsion, something that DOE is very familiar with because of Eric Nielsen's work, and then other launch environments and other CFD work. So there are applications that will need Exascale, but our charter is to support everything from small applications to big applications like that. Just to give you another sense, this is a timeline of CFD put together by Chet Michaelis in my division. And he's sort of talking about what has happened and what is going to happen going forward. So again, by the 2030s, one would expect that we need exaflop because we're going to do multi-physics with chemical reactions and so on and so forth in all the CFD applications. So I just wanted to give you a sense of the fact that we do have a fair number of applications which will require Exascale in the coming years by the end of this decade in particular. So what are our programming challenges? As everybody knows, hardware architectures are becoming complex with a lot of memory hierarchies and things like that. And also the programming models, there are a multitude of them. So choosing the right model for the right architecture is a very difficult issue for most of our scientists. As is sort of the apple pie kind of thing that users, when you ask them what they want sustainability for the long term, okay? So they want code portability. They don't want to be changing code every other year because the architecture underneath is changing. And obviously they want performance portability in the sense of that, hey, when we move to a new architecture, we should get at least the same performance, not a huge amount of increase in the performance. The problem is that we have a lot of legacy code bases, so hundreds of thousands of lines of codes which are 40, 50 years old in some cases. Our code base even now is about 40% to 50% Fortran based. A lot of movement towards C, C++, but we're still looking at Fortran as a major driver for our codes. And from the point of view of NASA, the focus seems to be on the results, the science and engineering results that you get out of these applications. And there's not as much emphasis on code enhancement, particularly for future architectures. So there's not much funding available. And also the expertise, that, as we can see, that most of the expertise these days is going towards data science and AI and ML. So even the universities are not producing what we would call computational scientists who could help the science and engineering users enhance their code. So what have we been doing? What is the current status that we have? As has been mentioned before, we understand that GPUs is a part to Exascale. So we've been trying to port to GPUs. We've been trying to encourage our users to port to GPUs. Unfortunately, there's not been a rush towards GPUs from the NASA folks. Few codes have been successful. Most of you are familiar with Eric Nielsen's group's work on Fun3D. Has used the DOE machines very successfully, but it was a multi-year, multi-person effort to get to that code. A couple of other codes have been successful, but it's few and far between. So even though we understand that GPUs is the path forward, it has been difficult, like I said, because of lack of funding to push folks towards using GPUs. We have been conducting some hackathons with the help of DOE and NVIDIA. And this has allowed some of the projects to start experimenting, building mini apps and things like that to get some level of performance improvement. But like I said, it is not a huge number of people trying to figure out how to port to GPUs. And that is obviously going to need to increase if you want to get towards the Exascale. We have been experimenting with the use of high-level frameworks, but again, this is a small effort using Cocos and maybe one effort using Flang with not much success. And also I've been trying to see if domain-specific languages, in particular one project has been looking at GEOS, the global circulation model of GEOS. This is out of NASA Goddard, our other supercomputer center at NASA. They've been looking at grid tools to help them. So what is our problem? Well, our biggest problem is access to Exascale systems. NASA's HPC budget has essentially been flat. And that would, what the result of that will be that it will be several years before we can even think about getting to Exascale systems in-house. The growth we see is fairly modest. Back in 2004, initial system, Columbia, was number 2 in the top 500 systems. Now, each of the 3 systems that we have are in the 80s in the top 500. And I was sort of doing a back of the envelope calculation that even if we combined all 3, we would be still, we would not break the top 20, even if we could. And that's because one of the problems is that our budget, instead of getting bulk budget for new machines, we tend to have a part of our budget every year being used for technology refresh, which means that we get a new architecture every few years, and then we keep incrementally adding on to it, which does not necessarily mean that we would get to Exascale very soon. And again, GPUs, we do have some amount of GPUs, but given the fact that most of our folks are still on x86, it's difficult to justify a huge budget for GPU systems. And then a lot of the folks have tried to actually access DOE systems to get to Exascale. And, but that's been difficult. It's a proposal-based system for non-DOE folks, and it has been difficult. Eric Nielsen has been pretty successful in utilizing DOE systems, but that's one of the sort of stellar examples, or the only stellar example. And there are a lot of issues to it, a lot of it on the NASA side, some on the DOE side. For example, given the fact that this is a proposal-based system, we cannot have access to DOE systems as in the critical path, because we may not be sure the next year we're going to get any more of the access. Or how do we get to the 20% baseline that DOE requires for the applications before they'll give them access? We don't have access to the sort of intermediate systems. So there's a fair number of problems in trying to get to Exascale systems at DOE. Going forward, this is mainly focused on what we can do with DOE and ECP in particular. Obviously, we are continuing to push for GPU support and porting our codes to GPUs. We have a small team of application engineers within the division which supports that, depending on who's asking for that support. And so what we're looking for from particularly from ECP is continued support for these hackathons. And in particular, one of the things that I'd like to figure out if we can get access to is what are the lessons learned and best practices that the DOE folks found as they were porting their codes to GPUs. How can we apply them to our codes, whatever the lessons were learned, whatever, how they managed to get the ports to GPUs. I did not talk a lot about the system software side. We are experimenting with E4S and trying to leverage modules from there, particularly looking at, for example, containers as we focus on on-prem versus cloud. So support for those kind of modules would be really helpful. And also high-level frameworks. I mean, like I said, we've had a small experiment with F9. It has not been very successful, but basically due to lack of sort of resources to apply to the problem. And at a higher level, which is not necessarily ECP's problem, is that I would wish we could get an interagency agreement between the two agencies for access to such leadership systems. We bring to the table our own experiences with hardware, which is unique to us. For example, the Luster file system. We have actually an MOU with Lawrence Livermore on the TOS operating system that we are utilizing at this point. And similar kind of collaborations would be really helpful. And I think that is my last slide. And I'll take questions now.
Thanks, Piyush. Excellent. So we have a couple minutes for questions, and then we set up a little discussion period here for about 10 minutes, just so we didn't do a whole wall of slides. So Mike and Eric, if you have feedback on the first three, feel free to bring that up as well.
I might mention one thing if I could. One is, I think all three speakers mentioned Fortran as something really important, and DOE, let's say ECP is in an interesting position in that we feel like the Flying project is essential for the vitality of Fortran going forward. And remember, Flying is just the front end, and it's the same technical and business model where everyone contributes to a common front end. Clang is similar, right? There's a common front end, and then all of the vendors take the LLVM backend and optimize it for their CPU or device or whatever it is. And so it's this really nice both technical and business model that supports contributing to things where common contributions on the front end are more valuable than competing with different versions of the front end. But then where the real value add, which is on the back end, you optimize it like crazy for your device. And that model is working really well for the C and C++ community. Julia is another instance of where there's that kind of same thing. And what we would like to see is the evolution of the Fortran ecosystem in that direction, and Flang is our attempt at doing that. And so so we've got this, but we don't have a lot of Fortran apps, and you folks have all the Fortran apps. And we need to set up a way for your needs to be signaled to the community, that so that we can pilot this ship in the right direction, the Flying effort. So it's more a statement, but I would love to hear responses from the first three presenters on that if they have thoughts, and others too. I see Eric Nielsen's on. I'd love to hear his thoughts too.
Yeah, so we have several benchmark codes that we use. We also have many apps that we can supply. The NASPARL benchmarks based on CFD has been around that people have been using for benchmark. Yep. And that can provide a fairly good target for Flang. to work with. And we can also have other codes, more sort of production level codes available for.
Well, if I might be so bold, we want people. Because we're trying to provide this next generation compiler front end, but we don't have the users who are saying, we desperately need this, or at least not very many of them. And it seems like you have the user community that could really make the business case for it. But we would really appreciate the people who would invest their time, not just the target codes. Those target codes are important, but the people are also important.
Yeah,
So
and
we could go ahead, Piyush.
Yeah, that's a little difficult, but we do have several active users because, like I said, most of them are interested in getting the results and moving on to the milestone and delivering
Understood.
the milestone.
Yep.
But yes, we do have certain interested users. If Eric is on, maybe he can speak a little bit. But Eric's team has done excellent in terms of porting to GPUs. And maybe he'd be interested. His is more C++, but there are other Fortran users that we could connect you with.
And we could certainly, from the DoD side, come up with some users as well. We have a number of people who are actively developing new Fortran code. We sort of have to find a way to make it, worth their while. That's always our sort of problem, is that, as Piyush said, our people are, sort of mission focused, and to try to get them off that and go towards, development of a different sort is a little bit of a stretch. But I think we could probably come up with some people for you, Mike. So, we'll see what we can do.
Thank you.
And Anshu, I see your, oh, sorry, did you just have something else?
No. Well, I was just going to observe that actually NOAA has the software environment, a software environment development project specifically targeted at novel architectures. And of course, the fate of Fortran has worried us now for years. And so we have started to play with the Flang front end, certainly started to play with the Intel version of it. But, if there's hope for Fortran, we want to make that investment.
Thank you.
So can I speak now?
Please, yes.
So I represent one of the few ECP applications that is Fortran based. And we found ourselves in this situation where we needed abstractions, but we didn't have the wherewithal to translate the entire code to C++, nor the motivation. So we started to develop a tool chain, and it's this tool chain that I want to bring to attention of everybody who has Fortran codes that they want to be able to use on heterogeneous architecture. We've built this in-house tool chain and we are seeing a great deal of success with it. So it has three distinct tools, one that lets you express a single source and mimics the behavior of template metaprogramming without actually bringing in the entire complication for it. Another is a domain-specific asynchronous runtime system. And the third one is a high-level recipe generator that describes the control flow. And using these three tools, you effectively get language-agnostic performance portability solution. So I'd be happy to talk to anyone about it. There is a poster that I presented yesterday. And I do think that we can provide a way forward for Fortran codes to not to have to wholesale convert to C++ in order to have performance portability.
Awesome. When we do a workshop, we're going to sign you up.
Please do. It's very recent that we've actually been able to evaluate these tools, and we are finding that anyone who learns anything about them is very greatly interested in them.
And I will say one of the lessons we're seeing from the application portfolio, and Anshu and Exastar is one of our sort of exemplars of this, is with Fortran, with the large legacy codes, particularly those in Fortran, there are no easy answers. So don't send anyone to a meeting or a workshop expecting us to give you the magic recipe. It is fundamentally, you have to commit to something, and it's a variety of sort of equally difficult and terrible answers, but depending on where you see the code going, you can adopt some of these advanced text solutions. And Fran mentioned the Rose compiler, which is Livermore, where I'm from, and as another potential way of, middleware maybe to automatically translate your source to different architectures. But and then other people are going a more conservative road with OpenMP offload. And these all have trade-offs. And I think it really is important to figure out what people are doing that's working and just sort of commit to a path, but do it thoughtfully. Don't assume there's only going to be one way to go, because there's a lot of ways you can do it, and they're all sort of hard in different ways.
Right. So our approach is to assume that there is a human in the loop who's doing the job of inferencing, so we've separated out the analysis and inferencing from execution, and we focused on building execution tools. So what can happen is that someone who understands their application really well can customize our tools to be able to use them, but what to do is still to be determined by the application developer. But what we enable you to do it without having to program to metal, once you tell the tools what to do.
Yeah, the most common story across ECP is abstractions are your friend, but again, for Fortran, they're harder to get at, and again, Anshu is our leader in that area. But it is, you have to sort of commit to that approach.
Yeah.
And Eric and Mike, I guess this is, a little bit of option for you to talk about some of the ECP efforts. I mean, Anshu did a little bit.
So I wouldn't mind addressing what Jeff raised in terms of workflow a little bit. And then just to broaden it, and maybe we'll save a bigger discussion with the panel for the end. But I think what you touched on, there's two components. There's the human time of complex simulation, and NNSA has been grappling with this as well. And this is what has generated the workflow, one of the workflow projects Mike referenced in ECP. But the other issue, I think, is a little bit bigger and scarier, which is that IO in general and viz and analysis associated with that are an iceberg we have not yet crashed into, because the model of simulation that we've been living with up until fairly recently is you do your simulation, you dump everything to disk, and then later you go dig through it. And that is, capacity is becoming an issue, the time to write that is becoming an issue, and then as Jeff mentioned, having the compute where you want it to do the post-processing is becoming an issue. So I think a question for everybody is, honestly, have you sort of looked at the IO side of your workflows, and are you going to be hitting an issue not just from the human side, but from the compute and capacity side? Because I think this is something we all should be thinking about now, because tech is going to be needed to fix it.
We certainly have looked at that, particularly for one of the codes, so MIT GCM, their code. It's produced about 5 petabytes of data. This is simulation, not just observation. We have a huge amount of observational data where we have the IO problem. But even for simulation data, we have tried to, for example, take 10% of the compute cores and just devote them to IO. Because, otherwise your whole compute gets all slowed down by the IO, which could have happened in parallel. And then how do you do post-processing? How do you do online processing? But this is only for one. It's not a generic solution that we found for this kind of problem. But it clearly is a big problem, and how to do that.
I wanted to mention real quickly that we actually spent a number of years partnering with a contractor by the name of Stellar Science to develop a workflow manager that we call Galaxy. And it does a lot of the administrative stuff, and it's actually been extremely well incorporated across our user community. And I'd be happy to send more information to anybody who wants to hear about it. But it's particularly our digital engineering folks have been extremely happy with it. And it takes a lot of the sort of grind away from what you're doing when you have complex workflows.
Great, thanks very much, and thanks, Eric. We have time at the end of our session here too for more dialogue, but right now we've got two other members, presenters from our ECP Industry and Agency Council. And Emily, if you're ready, we'd like to hear from you. Introduce yourself from NIH and let's hear what's going on there with Exascale.
Sure, I'm going to share my
perfect
slides here. Okay, so this looks good.
Yeah, it looks great. Thanks.
Okay, thank you. Thank you everyone for inviting me to speak and join this panel today. I'm Emily Greenspan. I'm from the National Cancer Institute in the Center for Biomedical Informatics and Information Technology. And I'm going to be giving some perspectives from the National Institutes of Health. So for those of you very, very quickly who may not be familiar with NIH, we're part of the Health and Human Services Agency, HHS, and we're made up of 27 individual institutes and centers, as well as the Office of the Director. The largest institute, NCI, is where I'm affiliated. Our current appropriation is about $6.9 billion for NCI. About 80% of NIH's total budget funds extramural biomedical research through grants, contracts, and other awards. So NIH takes a science and data first approach to thinking about advanced computing. We think about data science in terms of a data ecosystem. Components of this ecosystem include tools and analytics, data infrastructure, services like search and interoperability, workforce development, and community engagement. The vision is a modernized, integrated, fair, and that stands for findable, accessible, interoperable, and reusable biomedical data ecosystem. FAIR is important not just for parity of access to resources, but it's also required by science to assure the research associated with the data and software is reproducible. This is enshrined in our strategic plan for data science that was conceived a few years ago, and we're actually now in the process of updating it. NIH uses a distributed heterogeneous repository ecosystem that supports our extramural research community. For small data sets up to about 2 gigabytes, we have PubMed Central. For large data sets, we partner with commercial cloud providers, and I'm going to talk about that a bit more on the next 2 slides, but just to note that that cloud is a heterogeneous architecture, and to some extent, NIH wants to take advantage of new computing platforms regardless of scale. And then for the mid-sized data sets up to about 20 gigabytes, we rely on public generalist repositories, including Figshare and Zenodo. The NIH Science and Technology Research Infrastructure for Discovery, Experimentation, and Sustainability, or STRIDES initiative, allows NIH to explore the use of cloud environments to streamline NIH data use by partnering with commercial providers. And current partnerships include Microsoft Azure, Google Cloud, and Amazon Web Services. NIH's STRIDES initiative aims to modernize biomedical research by reducing economic and process barriers and utilizing commercial cloud services. These partnerships enable access to rich data sets and advanced computational infrastructure tools and services. Currently, STRIDES encompasses about 200 petabytes of data and has supported about 700 research projects and programs. I'd also like to mention, in addition to STRIDES, we have the NIH Cloud Platform Interoperability, or NCPI effort, that seeks to create a federated genomic data ecosystem and is a collaborative project among various NIH institutes as well as external partners. Connecting NIH's various data systems is a critical step toward improving researchers' access to various types of data. When researchers obtain data from a specific platform, there's no guarantee that the data will be readily usable and analyzable alongside data from other platforms, from different platforms. So by focusing on interoperability, NCPI effort is ensuring that researchers can both find and integrate data more easily from the 5 domain and disease specific platforms that are shown here. The one at the bottom, CRDC, is the Cancer Research Data Commons that is developed and managed by my center. So very quickly, I wanted to just mention NIH supercomputing. BioWolf HPC cluster that supports our intramural research program. BioWolf is still listed among the top 500 list, but it's currently on the November 2021 list at number 365 with a 2.5 petaflop RPeak. And this illustrates the dramatic gap of about 2 to 3 orders of magnitude between the scale of DOE exascale science and the typical NIH HPC user. This is very quickly just to represent the wide range of disciplines that where BioWolf is used. So I'd like to focus the remainder of my time on a specific collaboration that NCI, the National Cancer Institute, has with DOE. This collaboration is at the leading edge of the NIH community using GPUs. NCI and DOE have been working together since June of 2016 on an interagency strategic partnership. Last year in 2021, we signed a new MOU to enable a more sustainable and stable partnership. The Joint Design of Advanced Computing Solutions for Cancer, or JADAX4C program between NCI and DOE aims to advance cancer research through application of large-scale computing while providing design input for future large-scale computing systems to DOE through the application of complex, highly heterogeneous data sets. And we've been doing this, as I mentioned, since 2016, so about 6 years now together. We were enabled by the National Strategic Computing Initiative because NIH is one of the deployment agencies under NSCI, as well as the Precision Medicine Initiative. DOE contributes AI and HPC expertise and mission critical infrastructure, and NCI brings subject matter expertise and sources of real world and experimental data. We work together with 4 of DOE's national labs, Argonne, Oak Ridge, Lawrence Livermore, and Los Alamos, as well as with NCI's FFRDC, Frederick National Laboratory for Cancer Research, as well as several extramural divisions within NCI. The 3 main projects shown here, Admiral, Improve, and Mosaic, span across molecular, cellular, and population domains. And we also are building on established national priorities in important areas of cancer research, such as understanding oncoprotein, such as RAS activation, trying to develop predictive models for drug response, and building a network of population level cancer patient information. In the interest of time, I'm going to dive more deeply into 2 of these efforts, Mosaic, which is at the population level, and one of our cross-cutting technologies, Candle, which is an ECP application. The project is working closely with NCI's Surveillance Epidemiology and End Results, or SEER program, to greatly enhance the ability for real-time cancer surveillance reporting and improving the clinical trial design and feasibility assessment. For this audience, I'll just mention that the NCI SEER program is the largest cancer surveillance program in the country, and it encompasses data from about 30% of all US cancer patients, with plans to increase to 50% within the next year or so. The data that this project works with includes over 1 million unique cancer patients and over 3.5 million cancer pathology reports from 7 different SEER registries. Methods incorporate various cutting-edge AI solutions, including convolutional neural networks, self-attention networks, and large-scale transformer language models, uncertainty quantification, including incorporating abstention classifiers into the natural language processing deep learning models is critical for this project. These NLP APIs have been deployed in several workflows to SEER registries and have resulted in a significant time savings as well as a workload reduction for the human registrars. DOE infrastructure is critical to Mosaic. Mosaic is using transformer language models, which are currently the most powerful and state-of-the-art NLP models due to their inherent capacity to learn structural information from unlabeled text. Current transformer models are generally limited to short text inputs no longer than 400 words. But this is inadequate for this project because we're dealing with lengthy documents such as pathology reports and radiology reports that the SEER program relies on. So Mosaic's goal is to develop a pipeline for pre-training transformer models from scratch on biomedical and clinical text using the DOE supercomputing resources. Mosaic is currently doing this on Summit since Frontier is not operational yet. And they're also leveraging the Citadel framework for utilizing Summit on sensitive SEER data and informing how large-scale AI models can be scaled on the upcoming Frontier supercomputer. Since early 2020, Mosaic has been testing their transformer models on 3 generations of Frontier development systems so that Mosaic is ready to leverage Frontier on day 1. The project has already seen an acceleration by a factor of 3 on the latest Frontier development system and expects to be able to boost this further in coming months.
Emily, this is Susie. Just a 2-minute warning.
Okay, yeah.
Okay, great, thanks.
Just about done.
Thanks.
So Candle, this audience might be more familiar with Candle since it's an ECP application. It's an open source exascale deep learning environment that supports flexible workflows needed to train models in 3 cancer research domains, including cancer biology, drug response prediction, and text analysis for patient populations. Candle enables large-scale hyperparameter optimizations, model comparisons, and large-scale training runs of ensemble models and complex AI workflows. It's largely domain independent and can be easily adapted to use in many applications of AI across different domains in science and engineering. We've also been able to deploy Candle on the BioWolf supercomputer. So in closing, I just wanted to highlight some of the things that NIH would like to see and could benefit from going forward out of ECP. We envision a virtuous cycle of biomedical challenges driving computing innovation. Science challenges at the exascale level are envisioned to be such problems as in silico characterization of tens to hundreds of billions of candidate drug compounds, high accuracy characterization of molecular interactions and reaction dynamics, integrated multi-scale models using combinations of AI and simulations from cells to organisms across scales, studying multi-protein complexes on critical pathways and their interactions with cellular membranes, and understanding intracellular, intratumor, and other biological signaling. This is, of course, not a comprehensive list, but gives some ideas of what is envisioned. We need software that takes full advantage of the platforms NIH has invested in for performance, which involves GPUs in a heterogeneous hardware and software environment. For the NCI DOE collaboration, integration of GPUs in the HPC platform was a goal, and we've seen it pay off in terms of more complex simulations and better AI. But we need code that can balance across different types of architectures, so we don't have to continuously write new code every time a new architecture is designed. In addition, as I mentioned with Citadel, secure compute frameworks continue to be very important because a lot of NIH data contains PII and PHI. And that's all I have. Hopefully that wasn't too long. And I would just like to acknowledge several colleagues at NIH, Frederick National Lab for Cancer Research, DOE, and DOE Labs, who've helped me with this content and provided their insights and thoughts. Thank you. And I know these slides are available online. If you want to learn more about the capabilities, tools, models, etc., that have been developed by the NCI DOE collaboration, you can grab these links out of the box where the slides are and learn more. Thank you.
Emily, that was great. I think we can take one question right now before we move to Dan, and then we'll have additional discussion after. Does anyone have one quick question?
I have my hand up.
Oh, you do.
Okay.
I'm sorry, I didn't see
That's
it.
all right. No problem.
Thanks.
So thank you, Emily. I'm just curious, what kind of support do, say your typical users need when they're trying to use a software stack? Regardless of whether it's, you focused on the Exascale, Candle project and such, but in general, do you have a sense of, what kind of, support they need? Is it provided by, private companies that, specialize in providing these tools and workflows to them?
So maybe, I think Laura's on. Maybe Laura, you can help me answer this question as well. But I think that we need, it's really a lot about the data as well as the software for our user community. So I think there certainly are specialized tools, but a lot of the tools, a lot of the bioinformatics tools are in the public domain, right, through GitHub, etc. So it's, I think really a lot of it is being able to analyze heterogeneous data sets. Multimodal data sets are critical. Multi-scale data sets, having that ability to analyze and integrate without having to download to local machines is critical.
And then is the use of that software kind of, does the community as a whole teach itself and support itself in using those tools? Or do you actually have commercial companies who, specialize in, we do NIH software, if I can, something like that?
No, a lot of the bioinformatics software is developed by academics. We support various research programs that develop the software, and there are often grant networks or grant consortium that have training kind of built into their goals and milestones. So trainings are often a required component. Okay. So it's not, I'd say it's less so commercial partners and more so our extramural academic networks and consortia.
Thank you.
That facilitate that. Mm-hmm.
Yeah, thank you.
Doug, I think you had a question.
Yeah, this is really just a comment. Emily, just thanks for bringing up Candle. I just want to point out that the ACP has supported that effort at a substantial level. We're very proud of that for 6 years. And one of the panelists yesterday noted that we don't have any card-carrying machine learning apps where things like training rate are important, and that's not true. And you mentioned Candle and the transformer model, and we're really pleased to see that develop. It's been very successful collaboration.
It's been very successful, and we've benefited, and NCI has benefited a great deal, and we've heard from DOE that it's been beneficial for you as well.
You bet.
Emily, thank you very much. And we'll have time after Dan's talk for some additional discussion. Dan, why don't you take it from here? Are you going to be driving your own slides?
I can, unless David wants to. They are posted if anybody wants to grab them. So
whoever is driving, thank you. And Dan, please introduce yourself.
I'm driving, I believe. So thanks, Susie. I'm Dan Stanzione. I know many of you. I'm actually not notably from the National Science Foundation, but I'm their designated representative for this because I'm from one of the larger computing centers that NSF supports, which is the Texas Advanced Computing Center at UT Austin. So, and when computing questions come up at NSF, they often find their way to me. So when they're trying to weasel out of giving the talk, I get stuck with it. So that's what's happened here. And I'll try and be fairly brief, which all of you who know me know is uncharacteristic, just because I'm last, and therefore I'm going to repeat many of the themes that have come up so far. So I think most of you know this, or at least think you do, but the sort of computing landscape at NSF is such, and it's important to note, NSF is about a $7.5 billion agency. It is has nothing intramural, right? Its job is to advance science by handing out money. Essentially, that's probably a paraphrase of the official mission, but all the work happens primarily at universities, but at other organizations through grantees. But we do have a number of computing facilities that are funded through NSF. At the largest scale is the machine that I run, Frontera. That's pictured there on the right. It was the successor to a machine, Blue Waters, that many of you know at NCSA. And then the follow-on to Frontera will be something called the Leadership Class Computing Facility that I'll talk a little bit more about on the next slide. But it'll take us to about a half an exaflop, and that's where the very big computations run. There's another level sort of below that we used to call Track 2, but now has been Exceed, and Access is the new set of awards that were just made formally about a week and a half ago, but we'll take over from Exceed in August. And those are machines like Stampede 2 at Tech, Expanse at San Diego, Bridges 2 at Pittsburgh, Anvil at Purdue, Jetstream at Indiana. There's a few more coming online, Delta at NCSA, that are sort of for the, and those Stampede 2 is about 6,000 nodes. Most of the rest are sort of 500 to 1,000 nodes. You can think of them as sort of a capacity HPC component. And then there are individual computing and data investments in what are called the large facilities, or the MREFC type things, LIGO, et cetera. And so there's about 40 of those that NSF spends about $1.5 billion a year on operations for. And then they support through some various programs like the research instrumentation, MRI, or the campus cyber infrastructure, CC Star. There's dozens of smaller systems that get supported on campuses around the country that NSF also supports, but doesn't really manage, although some of those systems tend to provide some of their time through the Access or Exceed mechanisms. So there's a whole lot of computing support, and as everyone else said, not nearly enough software support. Well, really, there's not enough computing support either, of course, but the shortage is more extreme in the software side. So there are no specific plans in the NSF for an Exascale system. I will say the first LCCF system, which codenamed Horizon, that we'll be deploying in 2025, maybe late 2024, probably early 2025. So, it depends on a budget being passed on time. And since that has happened once in the last 30 years, I'm not holding my breath on that happening on time in 2024. So, we'll probably be in the 400 to 500 petaflop scale. The second one will almost inevitably be an exaflop, but there's never been any impetus at NSF at the science board level, the National Science Board, which sort of governs NSF, to actually deliver on exascale. It's deliver on the science requirements that are out there. So the good news on this is on at least the hardware side of things, the LCCF is going to be one of these MREFC major facilities projects that has a long-term funding stream. Things like the sort of bugaboo of the NSF projects has been, 5-year max with a 5-year renewal. But once you get into that major facility stream, the rules change. The Arecibo telescope was funded since 1964 by NSF through the facilities program, INCAR since 1959 through that program. So it does mean they're moving to a more sustained and consistent level of investment in computing, and hopefully that will reflect in some of the applications as well. The Access program, when it takes over for Exceed, there'll be various calls, and they tend to fund 2 to 3 systems every year, but they're sort of been limited lately to the sort of $5 to $20 million scale. So they're not going to be anywhere close to Exascale in the foreseeable future, but they may be the development systems in those technologies that you see moving forward. So, and then again, the drivers are the major facilities, IceCube, Neon, Large Hadron Collider, LIGO, Vera Rubin Telescope, et cetera, individual large PIs. And then we also see a fair number of applications from the other agencies because we do have this round of sort of capacity systems, and about 10% of the time goes to NIH researchers. And then through some contractual facilities, we have USDA, NASA, NOAA, even some DOE users on our systems as well. Just generally open science is the only gateway we use in the way that time is allocated. This came up earlier, at TAC, we put out about 8 billion core hours a year at this point, and the other providers put out about another 2.5 billion. So there's 10 or 11 billion core hours, if that's your metric, going to this at this point, and maybe a couple of thousand GPUs out there. So again, the problem with defining NSF exascale applications is not only are there no NSF exascale applications, there's no NSF applications, right? There's codes that belong to research teams that get some component of their funding from NSF, right, across universities and other large collaborations. So, so that makes this a harder thing to describe. So there are a lot of large applications though, and we regularly, we've had 12 of our research teams get above 400,000 cores at this point. I've had 30 teams get past 100,000 cores running on Frontera. So we know that there's a huge variety of large codes, but we also know that there are thousands of grantees, right? So, so we have, you know, NSF makes about 40,000 grants a year. 75 projects a year or so get time on Frontera, but about 2,000 get time on Stampede. So we actually have some analytics suites that we've built to look at the binaries, so we can figure out, you know, name of code tells you nothing. It's half the time it's A.out. So, but we've actually, you know, analyzed the binaries that run on the system, and we know we've had about 4,000 distinct ones over the first 3 years of Stampede. We have about 15,000 users who actually can run through a batch queue, through a production queue in Slurm. We have about 50,000 users once you get up that level of abstraction to sort of web gateways that hit what runs. So there's applications sort of all over the place. And the number of applications isn't our only problem. The bigger problem is people who run them don't necessarily have the resources to move forward. So the standard talking point is that the average NSF grant is about $145,000. That is the standard talking point. It's not necessarily relevant because most labs are better funded than that, but a reasonable size computational lab maybe runs on 350,000 a year in the university space. So a typical team is maybe a postdoc, 3 to 4 grad students. And yes, we can fit that into that amount of money. We don't have the overhead rate of a DOE lab. So, but most of those grad students who will make up most of the workforce are walking into graduate school with 1 or 2 programming courses under their belt. So, you know, templated C++ is not usually where they're starting. So, but the upshot of that is most of the software is open source, with about 85% of our workload, with about 15% commercial mixed in, mostly the CFD codes, and of course, LabVIEW, MATLAB type stuff. About 60% of the workload is community codes, but almost always the lab is making some local modifications, so we can't necessarily grab the newest fork of those. There's a fair fraction of the codes out there that are homegrown, but for the most part, the students who are working on them now didn't write them. You know, the 4 to 6 previous generations of students did, or grab them from somebody else. So, and we find that because they are grad students and the internet generation at this point, there's a pretty low tolerance for things that don't just work out of the box. So they maybe will mess with it for a couple of hours, but if you say, look up 900 things and move these other things, import code, it's just kind of a bad match. They'll just move to a system where things are easier. So even if they give up scale for that. So, so if we look sort of broadly, even our big applications, where we are is about 50%, which is actually a better number than it was 3 or 4 years ago, are GPU friendly. There's about 40% that have a real GPU advantage, you know, sort of dollars per flop. So, and that is, you know, still not good, but it's an awful lot of progress. And, you know, I think the GPU strides have been good, although it is almost entirely CUDA at this point. I would say porting to new models is a non-starter for about 70% of the teams out there, although our top, you know, 25 or 30% of our code teams are really, really good and can make very fast changes and are very innovative. Many of them are partners on ECP projects as well. But we also have sort of tens of thousands of consumers who are running codes built by others. And when they hit, say, an IO problem or an optimization problem, you tell them, well, have you looked at doing, changing the checkpoint interval or something like that? They sort of give you a blank stare back in response, like, I don't know anything about this code. So, so that's become an issue with, sort of doing support. Somebody asked in the last panel, how hard is it to support these users? I'll tell you, we have almost 50 FTEs who do nothing but that. Of course, we have, that gives them 1,000 users each, but and 10 or 12 of them are strictly in life sciences, mostly dealing with data prep. So around those NIH type codes, but our newer users are more likely to be familiar with cloud and web services. New computer science students can hook together web services at a very rapid rate. So we're seeing sort of these workflows of composable services, again, not often compatible necessarily with scaling up. As also mentioned in that sort of broader workflow issue, right, that demand for interactive use in those non-simulation runs, the AI, data exploration, Jupyter notebooks, and then saying, okay, now I have it right, I want to scale this up to by a factor of 1,000 instantly, has become a bigger and bigger component of what we see and what we have to do and deal with. So, so that's sort of where we are with where our users are. And so, if they didn't actually write the code, the odds of them ever changing it are fairly small. What we found is, even with community codes, they're always off on their own custom fork. And so a new version of the code comes out that doesn't necessarily lift all the problems. We've worked very, very hard in investing in making sure that when people do make these changes, that we build them back to the source tree. And in our funding, and as part of the LCCF effort, we just announced this week that we put about $7 million into getting codes ready for the next generation, where we're actually funding an extra postdoc in 20 of the code teams, 21 of the code teams actually, to sort of modernize things. We're staying close to the developers of all the community codes so that we can get things back up into the source tree, because what ends up happening is they have a custom version, if left to their own devices, that gets orphaned even if the main code moves on. So, moving from NWChem to NWChemEX, for instance, is a non-starter for a lot of the teams. So, so our needs from the ECP side, I would say where community codes, tools, and popular libraries are being enhanced, and there's a lot of great components through the ECP projects where things are getting rewritten and improved. That's undoubtedly going to be leveraged and utilized extensively throughout the sort of academic scientific computing community. It's fairly likely that all the NRE investments in hardware are going to get reused as well, but there's going to be a steep curve with the first gen of the Exascale system hardware. As I mentioned, almost all of the community codes, that even the ones that have GPU friendly code, are mostly CUDA code. So there's a lot of potential maybe to do something with HIP, but when we did the RFP for these projects that we funded a few months ago, of 150 so real applications that we got from different teams, asking them what they were doing with their codes, only about 1%, maybe 2% actually mentioned Cocos Raja or One API. 4 or 5 of them mentioned it. When we drilled down into it, there was 1 or 2 that had used one of those things. In terms of actual code implementation. So, I think the big message there is not so much that how many people have gotten working, it's that 97% of them didn't think it was important enough to even lie about and say they were making progress in any of those things at this point. So, which takes me to the last point, is that our ability to leverage all these things is going to eventually turn into your ability to leverage all these things, and training and workforce is probably the #1 area where you need to work with the NSF centers, because if I had to guess, 80% of the future DOE lab staff are going to come through one of these university labs that I mentioned that have at least some NSF support, and the rest will probably have NIH support. So from one of our agencies is going to be where everybody you hire with an advanced degree comes from. So particularly where your missions limit you to US persons. So we'll be pretty close to 100% of that. So being able to propagate this changes in the programming model back out will be the key thing. And so I'm probably close to the end of my time, so we will stop there and we can move to the discussions. Thanks.
Dan, that was really terrific. Thank you very much. Yeah, if you could do a stop sharing and we can get everyone back then. We're at a point now where we're just going to open this up for Q&A and broader discussion. We'll ask Mike and Eric maybe if you would like to kick it off with any questions you might have, but we'll be watching for other hands up or things in the chat that we can respond to.
Thank you. So yeah, as you see things come up, Susie or David, please let us know. So Dan, just going to yours since you just finished up, I think you paint a sobering and realistic picture of, I would characterize it not only just accelerators, but moving away from a sequential execution model under MPI. Is that an unfair characterization? I mean,
I don't think maybe it's quite that bleak, Mike, in that, whereas only 3% mentions Cocos Raja or one API in their application, everybody was MPI in that set, except one crazy one. And all but 2 or 3, so like 147 of the 150 were MPI plus OpenMP, right? So there's the notion of task level parallelism, thread level parallelism, vectorization. And again, on the order of the 20 we picked to work on, 12 or 13 have pretty good CUDA implementations, right? So there is the penetration of at least that idea. And obviously with AI, is almost exclusively GPU friendly at this point, where there's a blend of AI and simulation. So I don't think it's that bleak. It's just that it's sustained investment in a long period of time, because we're, 18, 19 years into the CUDA era at this point, and we're at like 60% penetration, right? So I think the notion that, there'll be broad adoption of a new model in the next 5 years is naive, right? But that things don't, but, if we'd done this survey in 1995, there would have been 0% OpenMP, 1/3 MPI, and everything else was sequential code, right? So I think, we need to put sort of consistent pressure to move the ecosystem forward, while at the same time recognizing that a lot of people aren't there yet. And that makes buying machines especially fun for me.
Yeah.
So I have a question for both Emily and Dan. You both referenced interest and use of the cloud in different ways. And it seems like, a lot of us are starting to re-examine the cloud as a way we should be looking at how we can develop software that's more interoperable and more usable. Have either of you, what are your thoughts in terms of how you'll write software going forward to take advantage of those resources? And is cloud something that you think is sort of a driver for you in your efforts in terms of just making things more accessible or having those HPC resources more available?
Emily, do you want to go first, or?
Oh, sure. Yeah. So I think cloud is really critical to NIH research. I was actually talking to Andrea Norris, who's the director of the Center for Information Technology at NIH, to help me prepare for this panel today. And, BioWolf is already pretty much outdated. The current version came on in 2018, and they're already looking to replace it. There are they're actually running pilot projects, about 10 of them, with Dan's Center TAC right now. So they're going to look at a partnership model where there's going to be some on-prem HPC, but really relying mostly on the cloud for interoperability. Cloud is really, really key for interoperability of our resources. We have highly disparate data, disparate across organizations and institutions, and disparate in types of the modalities and scales. And to derive new knowledge, it's really going to be crucial going forward to be able to make those tools, the software tools, and the data interoperable. And we see the cloud as key to achieving that.
So
yeah, I think. Oh, go ahead.
No, go ahead, Dan. You go ahead. I'll come after that.
Yeah, I was just going to say, I think there's a mixed bag there. I think, first of all, there's too many way smart people, you know, some of whom used to work for me at Amazon, Microsoft, Google, you know, who are real HPC people who are closing the performance gap. I mean, Nitro at Amazon, you know, latency is getting sub 10 microsecond pretty shortly. That, you know, the you know, sort of that rack scale level, which is rapidly becoming like 10,000 cores, is going to make a lot of sense. You know, there's not going to be a huge runtime difference in the cloud. There's still a huge cost difference depending on, you know, essentially cloud works if your usage model isn't to stress things 100%. But I think there are some programming innovations there we need to look pretty strongly at. You know, containers sort of came out of that. And for especially our life sciences folks, I think almost 10 or 15% of our cycles and 25% of the jobs are containerized at this point. And I know that's also an ECP topic, but you know, that's something we'll inherit from the cloud. The younger users learning cloud is our best way to ever escape from POSIX, right? Because the cloud solution to large scale parallel file system is to not do it, right? So, and it's our biggest problem in system reliability and everything else. So by just saying, nope, everything checks in and out of an object store and pay the extra cost for that, is a step that, you know, we've never been bold enough to make in the HPC community, but the cloud guys are just like, yeah, screw it. We don't see the case for that. We're not building you one, or if we, you know, you can provision one, but it's temporary and ridiculously expensive. So, you know, to be able to move to object interfaces for storage, that's going to come from the cloud. And then the sort of composable web service APIs are going to come from there too. So I think, you know, our notion of just, well, everything's 8 times slower in the cloud, that's going to go away, right? Because they will close the performance gap. But there are some things we can learn. But our cost advantage of having 100% utilized on-prem hardware is not going to go away in the next 10 years. So we're not going anywhere, but we need to learn some things from them.
One thing I forgot to mention that I should, when Dan jogged my memory when he was mentioned cost just now, I don't think NIH has really figured out sustainability in the cloud. So that's something we're starting to look into with the Cancer Research Data Commons cloud resources and cloud repositories, but it's a problem already. And if we don't figure out a way to move forward with that, it's gonna become a bigger problem. I think our agency accepts the upfront costs to establishing these resources, but doesn't necessarily accept the sustainability needs.
Yeah, I'd add to that, you know, there's a bunch of universities who said, you know, a cloud provider was the answer to research data, you know, perhaps with Box or Microsoft OneDrive, who have discovered in the last year or two that that was the demo rate, right? The first 3 years, and the cloud providers went from unlimited for a fixed amount to, okay, now you have 300 terabytes for the whole campus. And there's been a proliferation of tools meant to do multi-threaded fetch back from clouds, avoiding service caps, to get data out of Google Drive or OneDrive, as universities hit this cliff where the bill was going to go from $10,000 to $15 million in the next year around their affordable, sustainable cloud storage. It's sustainable as long as you pay the bill.
So from that's a perspective, I can echo most of the comments made by Dan and Emily. First of all, we have a lot of observational data that needs to be provided to the lay scientists and to the academicians and things like that. So we are heavily leveraging the cloud for the data repositories, putting all the data there and things like that. Again, like both Dan and Emily said, sustainability of that data, people have not really looked at that as the partnerships today are very cost effective from the data point of view, but may not be as we go along. From the HPC point of view, like Dan said, what we have found for our applications, the Amazon in particular, is almost the same as on-prem. There's no performance difference really on running on the cloud in large-scale simulations. But cost effectiveness is still a factor of 2 or 3 on-prem versus using the cloud for even simple MPI applications and things like that. Because we can be, 80% utilized and don't have to worry about the idle times and things like that. So our costs are about this. And this is when you actually don't even take into account all the support systems like the application teams and the software teams that you still have to maintain because you're only outsourcing the hardware. The rest of it you still have to maintain in-house for all of that. So, but the fact is that a lot of data is going to be on the cloud. So one of the things that we are pushing towards is a hybrid environment where not only do we burst out for using of the cloud, but we burst in from the cloud into the HPC environment, on-prem environment, in the sense that we have the data on there, and there's a big, huge data management infrastructure problem that we have that we need to solve. But things that we do on the cloud better, we do on the cloud. And then for the heavy lift analysis, we want to come back on-prem and do the analysis on-prem. So how do we link that? How do we manage schedule the jobs? How do we manage the data? Do we duplicate the data on both places? Do we cache the data? All of that is issues that we're trying to solve, but that is the push that we're making, that on-prem is good for large scale simulations, whereas the cloud is good for other things that, on-demand access, access to new architectures that we may not, as a government, it takes us a couple of years to get new architectures in-house. So go to Amazon and go Google and Azure to get access to those kind of systems. So we're focusing on a very hybrid environment, and containers are big, leveraging containers in there for that.
Piyush, just to follow up with the detail, if the hybrid approach, your users wouldn't see a lot of difference, right? Because they would have migrated to a container-based approach. Is that a fair assumption or not? I see Dan going. Maybe
I still have some heartburn with that, and we'd like to do this. And the data issues that Piyush mentions are exactly the ones we have to solve to make that true. Because containerizing the code is great, although mostly that's been to deal with like the software engineering side of things, right? Less module complexity if you live in a container. But our users still want to see their shared file systems, right? And there's many petabytes of shared file systems, and it's just not the tradition to also describe to us in your job file in your job script, every file that you're going to access on the file system so that we can make sure they're pre-staged and migrated, right? So until we find better ways to deal with data locality, in some of these, very data centric, like NIH applications where you might need to, live near the cancer genome atlas, we're probably better off shipping the container to where the data is stored than the other way around, right? But the one thing in cloud bursting that never seems to work in these hybrid environments is if you haven't well containerized your data. And so there are places where we've already moved the user to a web environment and we've sort of abstracted away a lot of the things where we can make that work. But for our standard command line user, it's like, hey, where's Scratch, right? And so, and if it's not there and they have to move it all, that, again, just adds tremendously to the cost and how long you have to keep instances running and stuff like that. So until we solve this data issue, it's really not transparent.
Thank you.
And if I could echo that, we have a number of our users who are testing stuff in the cloud, and one of them is a fairly large project that's looking at calculating storm surge maps in very gory detail, and the data is huge. And he's working on Microsoft Azure, I believe, and the only solution to move the data is to mail it in a hard drive. We have tried everything else and it's not possible. So, to me, that's a real world problem that we have to solve. And to still go back to what they used to call sneaker net, I think back in the day, where you had to actually walk the data around, that's not taking us in the right direction. So data movement is huge. I second that.
Thank you. I see Jeff has his hand up.
Sure. And I'll touch on this just because my group gets called when these things happen. But debugging and result reproducibility are another aspect of this whole cloud thing, which, yeah, sure. It's just a set of computers and my workflow software runs there. But when something goes wrong, trying to figure out what that was in an evanescent environment is going to be very, very hard.
Very nice. Are there questions from other members of the audience, attendees?
I don't see any hands up, but I may have missed them because we have to keep scrolling through the screens here. Does anyone else have any comments?
I have one more, but I'd like to pause and let other people.
Right. There was one in the chat for Emily. Let me see if I can go back. Maybe from Van No. Emily, do you have a plan for data sharing among collaborations and the public?
Yep, I answered that in the chat. So
did you? Okay,
I mean,
sorry.
Yeah,
I didn't
so
see
that's
that.
our, yeah, I mean, our NIH data, for the vast majority, I mean, our goal, our main emphasis is publicly accessible data. We have a whole, we're coming out in January 2023 with a whole new extensive data sharing policy. I can share, there's already like a pre website for that I can share. I have to dig it up, but that, I mean, that's key to what we support and what we believe in. There's certain, you know, sometimes certain data from certain CRADAs or certain clinical trial data can't be made public, but the vast majority of NIH research data is publicly accessible.
Great, thanks.
I wanted to ask about software ecosystems and any trends or say growth in the use of them, or is it steady, you know, in your community of users? In other words, what does the user depend upon that they didn't write or manage themselves in order to, you know, do their computations?
If I could start off, Mike, you know, my concern is that the software ecosystems are fragmenting among the different user groups pretty sincerely. And, you know, we have one group where, you know, nothing works if the kernel is more than 4 months old, you know, one set of groups, right? Whereas the others is nothing works if the kernel is newer than 3 years old, right? So, and you have to sort of simultaneously manage that, and containers help, but they don't completely solve the problem. I mean, you know, I think we have 5 versions of the compilers installed at the moment because of different bugs in each version that, you know, we have to work around. And that seems to be a problem that's getting worse, not better. And the downside of the container ecosystem and that sort of whole ethos around it is things like Anaconda and Python. And we see Python everywhere now, right? Even if it's just a wrapper, but almost every workflow has some Python somewhere. And its package management is so hellacious. The most recent example that HPC people would really appreciate is it has a nasty habit of adding lines to the bash RC file to copy files into a particular place. And so if you're running, say, I don't know, a hypothetically 2048 node MPI job, it'll do 2048 copies of those same set of files to the same destination location in the same shared file system. Which is just, and if you do 100,000 MPI tasks, you can imagine how 100,000 times copying the same data from the same source to the same destination is just an awesome behavior. So we've, you know, done some bash RC modifications to make sure that that only happens on rank 0 and that you ignore everything that Anaconda writes into bash. But it's from this, well, I live in a container and my container is my whole universe. And it's not possible that I could be talking to other containers off my laptop or a single cloud instance. And that kind of approach to software engineering is awfully fatal, particularly to file systems, when you start making 10,000 or 100,000 copies of stuff. And we see some version of that, it seems, every week. So, whereas at the same time, half of what those guys are doing is incompatible with the more, you know, it's the machine learning guys who need the newest stuff. But, you know, but that breaks everybody's old Fortran code. So the, you know, managing that tension seems to be a problem that's getting exponentially more complicated each year.
Interesting.
So I agree with that. I did a little survey just out of curiosity with our help desk folks and found out that something like upwards of half of the requests they get are searching around for old libraries or old versions of code that people need because the new stuff doesn't work for them. And that to me is taking two giant steps backwards in the HPC space, that it starts to become too unwieldy to try to manage all these not necessarily backward compatible versions. And it's, you know, I don't know what the answer is, but it's a definite issue that we have.
Same kind of issues that we have at our place, that people are looking for old compilers. I mean, reproducibility of results is so critical that they don't even want to change their compiler or anything like that. Libraries, big issue with libraries and versions of a library, which is the current version, which is the previous version, what they've used before, and things like that. So yeah, it's I think that's a critical issue of how to manage that. You have to manage multiple versions of libraries and multiple versions of compilers and things like that.
Well, we just have a couple of minutes here. Mike, I'm sorry, we started to talk together.
I just said
Did you have
thank you.
something?
That's all. Thanks.
Doug, I can't tell if you're still on. Did you want to, if you are, since we're kind of wrapping up here on this session, did you have any comments you might like to make?
Yeah, great feedback. There's a lot of work remains, so we're blessed with work. I guess I would say that, you know, from an ECP perspective, for our 5 agency folks here, I think we'd like to meet with you face to face and do a deeper dive into the areas that we've heard. Now that we can travel, I'm proposing that you know, a relevant group of us come to your place and we talk more about these issues. Some of these issues we share, and some we don't. And I think it'd be we'd be remiss not to spend more time with you. This has been a great session and a real eye opener. So thanks to everyone.
Well, Doug, thank you very much. I don't see any other hands up. If I'm missing them, please help. This has been a wonderful session, everyone. Thank you very much. Thank you to our agencies for your time today, coming and sharing your vision of Exascale for your agency. What are some of the stress points? Very helpful for us. Miranda, do I see your hand up there?
Nope, that was virtual clapping.
Oh, okay, sorry, virtual clapping. David, have we missed anything? Would you like to close us out? David Martin.
And I should unmute. There we go.
There we go.
Thanks everybody for being part of this. So it was a fascinating. I think we could spend a whole day at this, but as Doug said, we will continue the conversation with you. And we will hope that we get more feedback as we go along through the week. And feel free to send Susie or me email if you have other connection points you'd like within ECP.
Thank you.
And we were right at the time. So thanks to all our speakers. Wonderful session.
Thanks, everybody.
Thanks for the opportunity.
Thank you.
Thank you.
Bye.
Bye.